Yeah, thank you for the introduction. Hello everyone, I am Jeonghyeon from KAIST. Today we will talk about our work, revisiting partial tracing for safe, efficient, and concurrent garbage collection in unmanaged languages. Modern softwares are Yeah, then I will start. Okay, hello everyone again. I'm Jeonghyeon from KAIST. Today we will talk about our work, revisiting partial tracing for safe, efficient, and concurrent garbage collection in unmanaged languages. Modern software runs on more and more cores, so lock-free concurrency is now everywhere. It is great for scalability, but it is tricky to get right. Suppose we have a lock-free linked list on the heap. A reading thread, mutator 1, traverses the structure to find the key. And here it is accessing node B. While mutator is still using B, another mutator unlink B and frees it. Because nothing handled this reader-reclaimer race, the reader now touches freed memory, and we get a use after free error. The hard part is that this race has no compile time solution. Unlike single-threaded code, B has no static owner and no static lifetime for the compiler to reason about. So safety has to be decided at runtime. Managed languages like Java and C# already solved this. The compiler and runtime cooperate to provide an ideal environment for garbage collection. And we can see why using three criteria. First, it is efficient because compiler inserted safe points let the runtime coordinate GC paces with low overhead. Second, it is safe because stack maps tell the collector exactly where the pointers are, so tracing is precise and never frees a live object. And third, it is easy to use because the programmer writes no manual reclamation at all. So managed GC wins on all three, but only because it can lean on the compiler and runtime. Unmanaged languages such as C, C++, and Rust have no such support. So people usually manage memory by their own hand. The standard manual approach, epoch-based RCU, explicitly tracks in-use pointers. It protects a pointer before use and retires it to reclaim. On the efficiency criterion, this is excellent with very low mutator side overhead. But on the other two criteria, it fails. Manual tracking is well known to be error-prone, even for experts, because protecting or retiring at the wrong moment breaks the whole program. So it is both unsafe and hard to use. These are real use-after-free bugs from widely used Rust concurrency libraries. So even in unmanaged languages, automatic GC is highly desirable. Some automatic GC techniques already exist for unmanaged languages, and we can review them with the three criteria. They fell into two families: conservative tracing, like BDWGC, and reference counting, like CIRC. But unfortunately, both are not efficient, and each one traces away either safety or ease of use. Let's see why, one family at a time. Take conservative tracing first. It is inefficient because, lacking compiler support, it suspends every mutator with OS signals to get a consistent snapshot. That makes the program about 89% slower than the manual reclamation. And it is unsafe because without stack maps, it scans raw memory word by word for pointer-like values. When a live pointer does not look like 1, that false negative leads to use after free. But it is easy to use. Once it identifies the roots, it traces everything reachable, so it handles cycle for free. The other family is reference counting. It is inefficient because the count must be updated constantly. For example, as a mutator traverses the list, every single step atomically increments or decrements counts. Even the state-of-the-art CIRC is a recent scheme that optimizes this, but it is still about 55% slower than the manual reclamation. So the overhead of reference counting is quite fundamental. It is safe though, because an object is freed exactly when its count hits 0. But it is hard to use, because a reference cycle like E and F pointing to each other keeps the count first forever. So the programmer has to break such cycles by hand. To wrap up the problem, both families fall short, and the gap is clear. No existing garbage collection in unmanaged languages is efficient, safe, easy to use at the same time. And this is exactly what we deliver. Concurrent deferred partial tracing, a concurrent garbage collection library in unmanaged languages. Our idea is quite simple. Use reference counting only for the roots and tracing for the heap. First, we reference count just the root objects, the ones reachable from the outside the heap. Then, starting from those roots, we trace it through the heap. This design is safe because the reference counts identify the roots precisely without no fragile conservative scanning. And it is easy to use because tracing the heap still collects cyclic garbage, which has no external reference. So safety and ease of use come for free. But interestingly, this idea itself is not novel. A classic paper from 22 years ago already conceived this hybrid design and named it as partial tracing. So the only criterion still in question is efficiency. And here's the catch. Partial tracing has long been considered inefficient, which is why it was never adopted into a concurrent GC. That inefficiency has two sources. First, the original design coordinated its GC phases with a stop-the-word pass that suspends every mutator. Second, like reference counting, it constantly updates counts for root pointers, even though we count only roots. The roots themselves change all the time during traversal. And this is exactly what we fix. Our contribution is making partial tracing efficient through a highly concurrent design. For the stop-the-word pass, we make tracing concurrent with a stop-the-word-free mark-sweep design. For the high RC update cost, we follow the classic wisdom of deferred reference counting, which amortizes the cost of root updates. Together, these gives all three criteria at once. In this talk, for the time, we will focus on the first one, the concurrent stop-the-word-free mark-sweep design. First, some preliminaries on how the mark phases of mark-sweep GC work. There are typically two. The first phase is tracing. The collector marks the root, then traces the heap by draining mark stacks. In a concurrent setting, those mark stacks are distributed across threads. And the collector or the owning thread pops a task, marks it, and pushes its children until the stacks run dry. The second phase is completion. When the collector believes that no live objects are left to mark, it scans every mark stack, and if they are all empty, tracing is done. But once concurrency comes in, this is not so simple, because mutators help with tracing too. So a mutator and the collector can touch the same mark stack at the same time. That creates two data races, and both prematurely complete tracing. First one is late push. Suppose two nodes, one marked it and one not, and two threads run, the collector and a mutator. The mutator holds the only reference to B, so it tries to push B onto its mark stack. But before that push finishes, The collector scans, sees the stack empty, and concludes tracing is done. In this case, B was never marked, so it is freed while still being reachable. A user-free error. The second is early pop. Again, the mutator holds the only reference to node B, but a marked task for B is already on the stack. The mutator pops B to process it, which empties the stack, and it starts to mark the node, but before it finishes, the collector scans, declares tracing is done, B is freed, the same, user-free. The textbook fix is a stop-the-world pass. In both cases, the mutator finishes its stack operation before it hits a GC save point. So the collector only scans once the scans are consistent. This is correct, but it poses every mutator at save points to transition paces, and that serialization can cause a scalability problem. So we replace it with two concurrent mechanisms, pace consensus for the late push, inspired by epoch consensus, and concurrent validation in the completion pace for the early pop. Let's start with late push and pace consensus. The approach is to order every mutator push before the collector scan, while keeping the mutator side lock-free. The collector periodically advances a global epoch, which is a pair of a timestamp and a pace, stepping through normal, tracing, and completion pace. At each pace, the collector initiates that pace's critical collection work, such as tracing the heap or scanning the stack. On this foundation, each mutator opens and closes a pace critical section, and inside, it freely traverses the heap and creates a new RC pointer. Inside that same section, a marked task can be pushed to or popped from the mutator's own mark stack. This pace consensus then gives us the happens before relation we need. A push inside the critical section during the tracing pace completes before the collector scan during the completion pace. So any mutation of the mark stacks is always visible to the collector before it can conclude tracing. Concretely, the mutator is tracing inside the critical section during the tracing pace. It is about to push B. Meanwhile, the collector wants to advance to completion and scan. But it first waits for the mutator's open section to close. The mutator pushes B and ends its critical section. Now the collector scans and finds the stack not empty and resumes tracing instead of freeing B. Now the early pop, which we fix with concurrent validation. The core idea is a modification timestamp that captures a concurrent pop, and the flow graph on the left is the validation loop. From completion, we either succeed back to normal or fail and retry. First, during the tracing and completion pace, a mutator stamps a modification timestamp on a stack before it modifies the stack. Second, during completion, the collector does a double-checked read, like a sequence lock. It checks that all stacks are empty and that no stamp matches the current timestamp. Concretely, the mutator is in a critical section during completion with B on its stack. Before it pops, it stamps the stack with the current timestamp, T+2. It then pops B and tries to mark it. When the collector validates, the stack itself is empty, but the stamp equals to the current timestamp. So the check fails and the collector resumes tracing. Putting all of these building blocks together, CDPT becomes the first scheme to get all three criteria at once: efficiency, safety, and ease of use. And we backed that efficiency claim up with micro and macro benchmarks. First, for the micro benchmark, our target is lock-free maps. Multiple threads call get, insert, and remove call while we scale the thread count up. which is the workload that stresses reclamation hardest. Our most striking result is tail latency. Among the automatic schemes, CDPT keeps the tail latency by far the most stable. At the far tail, the P99.99, CDPT cuts latency about 6 times compared to reference counting, and about 32 times compared with conservative tracing. Throughput tells the same story. CDPT in red outperforms both automatic schemes in purple and blue, and stays comparable with handwritten reclamation, all while remaining fully automatic. The one honest trade-off is memory. Because CDPT traces the heap before collecting, it uses more memory than manual baseline, but it stays well below the other automatic schemes. So the overhead stays reasonable. Finally, to show this holes beyond a micro benchmark, we turned it to Mocha, a production-ready Rust cache library. We ran the YCSB benchmark, and we replaced Mocha's handwritten epoch-based reclamation with our CDPT algorithm. That removed every manual reclamation call and unsafe access block, a net reduction of 120 lines. The result is that on workload A, throughput moves by about 0.25%, and P99 latency by under 1%, both within noise. So in a real-world application, we can swap a handwritten reclamation for our automatic one with no visible performance penalty. Yeah, so to wrap up, CDPT revives partial tracing as a concurrent GC library that is efficient, safe, and easy to use. The paper has much more details, such as optimizing local routes using hazard pointers, and hybrid write barriers for correctness, and type-safe Rust API, and even more. And everything is open source at the link on the right. That's all, and I'm happy to take any questions. Thank you.
Thank you, very nice talk. So how would you differentiate your work from taking one of those already existing concurrent GCs, for example, Ghost GC, or there's lots of Java GCs out there, implementing in Rust and comparing that to your work? Like, what differentiates your work from all existing GCs?
So first of all, thank you for the good question. And as I said in the early slides, those conventional garbage collector relied on runtime and compiler. And in those many languages, those garbage collector needs GC save points and precise tag maps to work correctly. But in our setting, those kind of infrastructure doesn't exist. So basically, we need to find another approach, and our work is one of them. Yeah.
Okay. I see. Thank you.
Oh, yeah.
Question? Oh, okay. Yeah, quick follow-up to that one. What about with Rust? When you're supporting Rust, that is, because there, in principle, at least, you do have stack maps and so forth, in principle, in LLVM.
So are you mentioning some LLVM experimental feature like stack maps?
Yeah, I just mean that when you've got a well-typed language, for C and C++, it makes, what you're saying makes complete sense. But once you get to a language like Rust, in principle at least, it's a different story, right?
Yeah, so I guess that approach will require accessing the compiler level knowledge. So I think that will have a trade-off, but our approach is purely library-based, and yeah, and which is portable to other code base very easily. Yeah, thank you.
Time for one quick question. All right, thank you.
Yeah, thank you.